It's an honor for me to be here in this event. At the beginning, I was thinking in a different topic for the presentation. However, as I see the program and how important are the topics related to the quantum effects in the event, I just decided to talk about the most important experiments that I've made in my lab. That is the two-way mixing and eventually the cell diffraction effects derived by the ordered nonlinear optical properties in nanostructures. Well, the outline of the talk is quite brief. It's an introduction about the nonlinear optics, then the two-way mixing, and how is generated the optical Kerr effect and multiphotonic absorption, and then the influence of a magnetic field in nanostructures with potential applications for the development of ultra-fast all-optical devices. Well, these are some photographs of the labs where my collaborators work. At the top, we have the Pelletron accelerator in UNAM. We have the preparations of ion implanted samples in the accelerator, and then this is a photo. I think maybe there's so much light. It's the ultra-fast pulsar laboratory in CICES in Ensenada. Then in Penn State University we have a collaboration with the physics department, and in the ESIME, it's my lab. You are welcome in any occasions to go to visit our laser systems, and the nanoscience center for characterization and preparation of stuff. Well, to start with the presentations, I would like to think with you in the emotional impact that we have when we think in the double slit experiment. I think all of you know the implications of these results, and many of you, the first time that you knew about the modification in the behavior of a particle or a wave in this experiment, think that it's difficult to believe. Particularly for me, when I was a PhD student, I remember that when my professor told me that it's possible to make darkness with light or interference effect, I didn't believe that until I see in the laboratory. Many people that we know, our family, people from some friends, when we talk about this, it's very difficult to get familiar with a conversation or with the concepts about quantum effects and the effects that happen in nature or in macroscopic situations. In the way to see this experiment in low-dimensional materials, thinking about architecture, that is constructing something in the space, we have different possibilities to construct nanoparticles. I think there is a very important property related to metallic nanoparticles that is called the surface plasmon resonance. Surface plasmon resonance is an effect that is only observed in small regions of the space, and it can be indirectly measured by a spectroscope. Is the illumination of a metallic sample, with nanoparticles, and the particular absorption related to this surface plasmon resonance is located in a wavelength that depends of the metal. For instance, this is the peak related to the absorption band of the surface plasmon resonance, that is a collective response of the electrons related to the materials for silver. But for gold, we have this peak in the green. For copper, we have in this region. For platinum, for instance, we have in ultraviolet. For nickel, we have in the blue. So the modification of this peak is derived by the modification of the preparation of the sample with elements, with the size, with the shape, with the distribution, and eventually we can prepare a sample as we wish by using systems like laser systems. As you can see here in these experimental results, the blue one data are related to as prepared sample that is prepared with the machine that I showed you at the beginning of the presentation. That is the pelletron accelerator. It's like a gun that impacts in a substrate, and then the elements in the substrate are integrated as a nanoparticles. Then they have this response, and when you use a laser system, you modulate this response and you modulate the shape of the material.
I'm sorry, because the time that you use to radiate the sample?
Yes, no, this is a pulse. It's a single pulse. Just one pulse at this wavelength, and then you modulate it. So when you have this material, you can control with the absorbance the transmittance of the material. Then if you can control the transmittance of the material, you can use these optical transmittance to make, for applications, for instance, medical applications, telecommunications, instrumentation, for measuring and characterization of materials. This is a collection of applications that can be related to these systems, laser system, that can be controlled by nanoparticles. So eventually a laser system is used to make these things, eye removal, eye surgery, facial plastic surgery. And with nanoparticles, you can modulate the transmittance of the beam in ultra fast time. This is very important because you can eventually damage for different regions by the regions that are not located in the incidence of the spot, but the propagation of the heat can damage collateral regions of the incidence. And if you use nanoparticles, you can control the laser system ultra fast and avoid these problems. Some of the, as you see this in this image, some of the characterization of the nanoparticles are made by microscope, electron transmission electron microscopes, and the size of the nanoparticles can be as small as a few nanometers. Here we have a representative image of gold nanoparticle prepared by ion implantation. This is prepared by a chemical Solheim technique. These are prepared also by ion implantation, but we move the material in order to obtain an anisotropic sample, and eventually, if the light, as you know, the light has a vectorial nature. If the light has the vector of polarization in this direction absorbs in a different way if the polarization is in the orthogonal polarization. We have here, these are also gold nanoparticles. These also are gold nanoparticles, silver nanoparticles, platinum nanoparticles, gold, and this is a bimetallic nanoparticles. We see that if we have the control of the light in the particular sharp selective resonance of the metal, if we use a different metal in a bimetallic shape, we can make an isotropic nanoparticle like this one, almost quasi-spherical. But with different elements, you can control also the transmittance, because it's going to be different if the light goes first with the one element or with the other one. So in the energy dispersive X-ray spectroscopy, these atoms correspond in the same nanoparticle to gold, and here to platinum. These are lithium doped oxide side. And in our group also we prepare carbon nanotubes. See, these are carbon nanotubes, and we put nanoparticles in order to control signals. This is another image. I think the platinum nanoparticles are the bright points in the image, and silver nanoparticles. Okay, now about the experiments. I think the most simple experiment for nonlinear optics is the transmittal experiment. Eventually we're going to arrive to the double slit or multi-slit. We have a sample, and if we measure the transmittance and the reference of the incidence of the light, we can obtain, well, this is the okay, this is what I want to show you. The transmittance, if we increase the incident irradiance, the transmittance should be constant if we use low irradiance. As you increase the irradiance, it should be linear, the increase. But in nonlinear optics, this is not true. In nonlinear optics, as you increase the transmittance, it is possible that there is a decrease in the rate of transmitted irradiance or an induced transparency. This is a quantum effect. So if we have, for instance, I think this wall, why we cannot see to the other side of the wall? We don't see because the photons that are outside goes to the wall and they are absorbed, so we cannot see. But let's suppose that we have a laser here, and then we illuminate all the wall, and we complete the absorbance of all the atoms there. If we complete all the absorbance, all the potential absorbance of the wall, there is not going to be the possibility that another photon can be absorbed, and then we can see the photons that comes from outside. So this is the transmitted irradiance for an induced transparency, and eventually, well, this experiment is made on the basic laboratory. You can make transparent materials or multiphotonic absorbance. You decrease the transmittance when it's possible that an electron, let's suppose in the band of that diagram, we have in a level or absorbance, it's possible to make a quantum jump to a different level. When we use light, the absorbance is made by quantum jumps of the electrons. So in light, I mean the electromagnetic waves that we see, the materials produce quantum jumps of electrons. When we use wavelengths like microwaves or like infrared, there is not quantum jumps of electrons. There are motions of the molecules. That's why microwaves often are useful because the microwaves move the molecules and then they hit the food. If we use shorter wavelengths, we don't make all neither the molecules of motion, neither the quantum jumps of electrons is produced. It's generated the motion of the nucleus of the atoms, and then eventually it can produce some problems if, for instance, in cells or in another materials that can evolve or chemical, or because it can eventually be chemically active. So now the two-way mixing experiment. So if we make an interaction of different beams with the same wavelength and the same polarization, in the superposition of the two beams, we have an interference pattern. So if we produce this superposition, it's possible to make this kind of damage. The lines are related to the period of the wavelength that you use for the incidence. But if you, instead of using a material that is that absorbs strongly the light, you use semi-transparent material, well, there is a possibility for linear refraction, linear absorption. A quantum jump can produce a phonon delivered by the incidence of the photon, or multiphotonic interactions can be related to the optical Kerr effect or the nonlinear optical absorption. So in the case of, for description of these two different effects, we have a tensor related. The real part is related to a modulation of the velocity of the light, and the other one, that is the imaginary part, is related to the absorbance of the light. It produces the optical damage, but also it produces a grating in the material. You can make this grating as you wish, depending on the angles of the beams, of the wavelength, and of the intensity. The polarization also produces a contrast in the interference pattern. So now we have not two slits, but many slits in the interaction of two different beams. So now what is going to happen when a particle, that can be energy or material, is going to interact with this grating? So if we have this grating that is modulated by intensity, the index of refraction of a material is related to a constant and to a property of the material and the intensity. So the index of refraction, if this represents the spot of the beam, is going to be modulated with dependence of intensity for the refractive index, and also the absorption that is related to a constant, and a constant related to the material product with intensity. We have two different gratings in the same region, one for refractive index and one for nonlinear optical absorption. So this grating generates diffraction. So when we have these beams, eventually the energy is going to change the direction. And we can consider that the stronger energy transfer comes from the energy that goes from this beam, goes to this beam, and the energy from this beam goes to the other one. So the energy from here is going to here, and again this here for here, but also it's going to be a part that is going to be outside, it's the self-diffraction, and outside in the other side. This is like the natural effect that you can see in the moon, when we have a cold night. Sometimes the moon is surrounded by a halo. This halo is related to a self-diffraction that is originated by the very cold particles in the atmosphere, and the light originates a circle, that is eventually this circle and this circle for this beam. For the mathematical description of this effect, okay, there's an entanglement quantum entanglement that is originated in this experiment. So the self-diffraction beams are related by the effect of the nonlinearity of absorption and refraction. And the description for the propagation of the beams is fractional. So if we have the Schrodinger equation and we make the fractional Schrodinger equation and we solve or we propose a solution for the Gaussian beam in the interaction, we obtain that there is a generation for each beam. There is a transmitted beam. The transmitted beam, we have a different beam that corresponds to a self-diffraction. So in the experiment, well, in the lab, we have a laser system to be split in two different beams, and we use a wave plate, a half wave plate, in order to control the polarization of the beam. A wave plate originates the rotation of the polarization. So let's suppose that we have, okay, the direction of the beam is in this direction, and the direction of polarization is perpendicular. So the wave plate allows you to rotate this vector. So eventually we put some photodetectors for measuring the transmitted beams and the self-diffraction beams, and the self-diffraction effect is going to be dependent on the nonlinearity that is characteristic of the material. For instance, the material can change the physical mechanism of nonlinearity from thermal to electronic to molecular orientation or electrorestriction. So we can test with this technique the physical mechanism responsible for the nonlinearity of the sample in the system. Okay, we're going to consider the response for three different laser systems. We have a nanosecond laser system with 4 nanoseconds per pulse, 25 picoseconds, and 80 femtoseconds in different wavelengths. The fundamental of the neodymium laser system is 1064. Then the second harmonic is 532, that is green, and the third harmonic is 355 wavelength. And well, something that has to be said is the nanoparticles. The response of the nanoparticle depends also on the surrounding. It's not only the shape and the size and the distribution of the surrounding. The same nanoparticles present a different response of resonance. Actually, you can quench the resonance if you change the material also in the environment from ethanol, nanoparticles suspended in ethanol, to a thin film. And if we plot the direction of the polarization here versus the cell diffraction signals, we see different data related to the different materials, even if it is the same nanoparticle. And the Kerr transmittance can be tested by the change in the phase matching of the beams. So let's suppose that we have two pulses. These are in phase match, but eventually you can delay one. If you delay one of the beams, you can estimate the temporal response of the systems. when the temporal response of the curve transmittance is equal to the pulse, it means that the temporal response of the sample is faster than the pulse. In this case, this is a femtosecond pulse, not picosecond pulses. So the sample must be with a temporal response faster. And something that also happens with these samples is that when you use, for instance, the green wavelet for testing the sample, if you see the right part of the absorption bands or the source of plasma of resonance, you're going to obtain a sign in the for instance negative sign in the response of the nonlinear optical refraction, and in the other one, if you use a wavelength for the other slope, you're going to change the sign, so it's going to be positive. For instance, negative refraction can correspond to thermal, and positive can correspond to electronic. So you can change the mechanism of the interaction with the light and the material by changing the surrounding. In this case, for this is silica, and the other one is titanium, the surrounding of the same nanoparticle. So if you can't change from positive to negative the refraction, the induced refraction of light, you can accelerate or you can delay the propagation of light by the same sample. So you can put like a sandwich, and then eventually to control the different speeds of the light with refraction. Or you can use different samples. You can use, for instance, here, it corresponds to silver, and it corresponds to gold. So if you use a wavelength, for instance here, a wavelength like here, you obtain a sign for the silver and a sign different for the gold in the same system. Or eventually you also can modulate the shape of the nanoparticles. For instance, these are RBS experiments. These experiments are made in the same pelletron accelerator. So the pelletron, let's suppose that this is the sample, and then we have the accelerator, and then a particle impacts to the sample, and there is a collision, and the projectile goes to change the direction, and you detect the energy of the projectile, and then with the energy that you detect, you can know what element you have in the material. So you can use this instrument and eventually to measure, if we have, for instance, here oxygen, silicon, silver, oxygen, silicon, and gold. These are the two samples that we are considering for the evaluation. And we have asymmetric shapes, and with the asymmetric shapes you can see that you can change the slope of the peak of the absorbance related to the source of plasma of resonance, and eventually to use them for change the speed of the light in a system. Well, these are some experiments related to wave mixing. Just to compare, the experiment in ultraviolet with the green, it corresponds to silver, and the difference is related to the absorbance spectra, because when you test the sample with ultraviolet, the absorbance is big and the refraction is small. When you test far from resonance, the nonlinear refraction increase and the absorbance decrease, as you can see. It can be deduced from the spectrum. And also, well, we can compare the response from silver and gold for the same wavelength, that is green in this case, and The response when you put, this is for the blue one, this one is for gold, this is for silver. The red is when the beam impacts first the silver and then the gold, and then you can see there is no response if you change the direction of the sample. This is because they have different sign in the nonlinear refractive index, and also the phase of the beam is going to be changed by the use of different nanoparticles. When you put in the sample a different element, for instance platinum, you can switch the position of this peak, as you can see in this spectrum. But also, you can originate a different peak with the same sample. So it corresponds to platinum and it corresponds to gold in a bimetallic sample. This is a demonstration of the gyroscopic response of the sample. If you have the modulation of the position in the testing, you can see that a change in the absorbance is going to be obtained from the modification of the position of the bimetallic sample. So these are some spectra of the platinum in order to see that the plasmonic response does not appear when you have small nanoparticles, but there is a size that allows you to obtain the plasmonic response and the ultrafast response of the platinum. When you have a modulation of the nonlinear refraction in the sample, you can modulate also the structure of the light, and eventually you can obtain twisted light. So if you change the nonlinear refractive index in the material, you can also control the momentum of the light in different directions for quantum applications. And the second part of the talk is related to the same experiment, but with the influence of a magnetic field. So we have a magnetic field in different directions. This is the sample. The two-way mixing is in green. In red is the proof. Is the proof beam. And okay, this is the equation for the transmittance that is related to the permittivity and permeability and the impedance. And this is the spectra of the sample. These are carbon nanotubes, and carbon nanotubes with the participation of platinum decoration. The conductivity in the sample produce a magnetoquantum conductivity. This is a nano effect that is related to an increase in the magnetic field to get a peak, and then a decrease of the conductivity with the change of the magnetic field. This is without light. But with light, okay, no, this is also, but with the decoration of the platinum nanoparticles, you can modulate the response of this conductivity. It depends on the amount of nanoparticles that you put in the nanotubes to change this effect. And eventually the participation of the platinum also originates a change in the energy transfer from a beam from an optical beam in the sample. So when you don't have platinum, you can originate more heat in the sample and decrease this or accelerate this energy transfer by the incorporation of the platinum nanoparticles. This is the change in the refractive index by the incorporation of platinum nanoparticles. You can see that temperature can change in a different tendency when you put the platinum nanoparticles in the carbon nanotubes. And in the two-way mixing experiment, the magnetic field originates a decrease in the transmittance. I mean, you can switch the signals in the two-way mixing, and eventually to modulate the optical response of the system, controlled by a magnetic field in an all optical experiment. Here we have the response of the plasmonic nanostructures, the response of the plasmonic nanostructures with magnetic field, and the carbon nanotubes. As you can see, the carbon nanotubes can be enhanced by platinum nanoparticles or by a magnetic field. Okay, and the conclusions are related to the self-diffraction that can be useful for applications of controlling light and energy transfer mechanisms. Well, some reference and acknowledgements for my collaborators, main collaborators from CICESE, from UNAM, Ensenada, from IFUNAM, from Universidad Iberoamericana, Penn State, University of Hidalgo, from the Center of Nanoscience of UNAM, Universidad de Valle de México, TESCO, Universidad de Chile, and these are part of my group in ESIME and Instituto Politécnico Nacional, and my students who are responsible for many of the experiments and plots shown in this presentation. Thank you very much.
Questions? Sarah, please.
I am interested in the production of right?
Oh, yes.
How is the cost of the production? Because we are introducing some carrier gaps and walls or bases walls which have but I'm wondering if it is really expensive or the technique that have to change the particular place is efficient in the production of just one mode or maybe introduce to produce different or modes on demand. How is it?
I think it's not too expensive to prepare the samples. It's quite easy. Sol gel technique, for instance, is very easy to prepare this system because it's only a gradient of the distribution of the material in a substrate. It can be a simple substrate like a glass. Nevertheless, the problem is to obtain the resources for guarantee the shape of the twisted light. I mean, what is expensive are the systems to test, the detectors or the laser systems to prove that there is a light. But once you have the infrastructure for measuring, I think it's very cheap.
But it makes supposed to use those to check if you are being correct and
Well, yes. Well, we had a problem with this because in the laboratory that was taking this research, we have a picosecond laser system that the pulses can vary from 1 hertz to 10 hertz, and the system that allows us to measure the twisted light requires a laser system of a very high frequency of repetition. So at this moment we are trying to make a collaboration to use or the detector with another laser or to obtain a detector with the laser that we have. Then after that I think I can answer how easy it is to control that property that I think is very important. Well, it's like megahertz. the detector requires megahertz. So actually, there are many laser systems with megahertz. We have another one, but it's in Ensenada, so it's not easy to make the collaboration, but we're trying to do that. Thank you.
Questions? Please.
Thank you for your talk. I'm seeing that you are playing with the dark states of light and
Yes,
interaction with
exactly, yes.
per sample. Have you tried to integrate with different degrees of freedom? I don't know. You are producing now twisting states of light or momentum, mass, speed, things like that.
Well, it would be attractive to take into account the different parameters, but in our group we are focusing in the phase and in the vectoral nature of light. Only that, the polarization and the intensity in order to obtain all optical switching, amplification, or phase matching. But we want to take with a very welcome recommendation. Thank you.
In your experiment, the cell diffraction, can you make this experiment with low intensity, for example, using Fox states of light?
Yes, it's possible. It's possible. There are many people in India, I think, do this experiment with laser pointers, but they have organic materials with a strong nonlinearity. The problem with the strong nonlinearity is that the temporal response is slow. Actually, when I was making my PhD, we have in the laboratory we have a carbon disulfide that is the standard material for calibration, and it was very hard to see the cell diffraction. I think it takes me about a year, maybe 1,000 experiments to see the cell diffraction. But at the end of the lecture of my thesis, one of in the public bring a sample, and he says, let's go to your lab and see this material. And he put the material in the experiment, and it was like a sun. It was possible to see several diffractions. It was made of nanostructures. So probably the solution is to prepare advanced materials to make easy experiments and not require so strong infrastructure or high intensity.
Questions?
I have one. Concerning the fractional expressions you require to explain some of your pictures.
Yes.
The fractional parameter is connected with what in the laboratory with your experiment?
Okay.
Because you model something with
Yes.
fractional.
Yes.
Sorry.
Yes. So the fractional parameter is where alpha can take different values and depends on the energy transfer. So in the case of the cell diffraction, it takes the value of 1. I think is the 1/2 of the derivative to model this experiment. However, when we have, for instance, production of heat in the material that it has been measured also in my lab, we need to adjust this fractional parameter in order to model the response of the energy transfer. The transformation of photons into phonons. So it has been made experiment.
So that you have the phenomenology
Yes,
and
exactly.
then
Yes,
adjust
we fit
the
yes,
parameter.
Exactly, that's what we mean.
And in the opposite direction is perhaps possible to make some experiment in which you can tune the physical property of the light you are using in order to adjust to the parameter alpha. I mean, is it possible to do that?
I think yes, but I don't know how to do that. Yes, it should be interesting to propose first in the theoretical case, and then to look for an experiment. For instance, there is an experiment that I think that changes this parameter. That is when you use a third beam. So in with the participation of a third beam in the interaction, there is a generation of additional gratings. There is the grating of the absorption and the grating of the Kerr effect, that is the refraction. But with the participation of the other one, there is going to be a different grating, and this actually is used for military applications, because when they have two different beams, and the additional beams comes from the target, automatically is generated in the energy in the direction of the beam that is taken. I mean the objective. So we have the two-way mixing. We can use it. We have the two-way mixing, like I wrote, and then we have a third beam that is the objective of with the purposes that you want, and automatically generated a different beam with the intensity. This can be strong intensity, and you can produce ablation. So I think with the participation of this one, there is generated an additional grating that I think is not possible to is required to change the parameter of the mask. I think it would be nice to try.
Yeah, my question is because perhaps you might, for example, you might have some models using fractional calculus, and of course we have all the analytical solutions and so on. And we are looking for specific applications for this. This is why my question.
Well, I would like to see if possible, we would like to talk. Answer that.
So we have to manage to control
it would be very nice, if possible.
Okay, more questions? No? Let us name again our speaker, please.